how does that work? I mean, are you curious? What happens to when you get a Nobel Prize? Right? Every one of the scientists have imagined, oh, maybe one day it's me. So he gave a talk about what it is to go to Stockholm and receive that prize. That was the whole talk. It was full of pictures and how, how that was arranged, or how did they decide who will go with him, of course, beyond family, etc., etc. And the talk was beautiful. It was really wonderful. He entertained us with lots of pictures. And then he looked at us, and as typically happens in colleges and universities, the senior-most people in the department, professors, sit in the front. The students like us were sitting at the back. So what he did was, he walked 2-3 rows like this. So all the professors were behind him. And he said, all I said today was really for you. These people have no chance. So I see that there are lots of young people sitting there. And truly, I don't know about the Nobel Prize, but I truly want those younger people to look at this talk as potential where you could actually contribute. Because this machine, as I'm going to tell you, will be built in about 10 years. And typically these big machines take 30, 40 years to come from conception to realization. That's typically a large machine like CERN or at Brookhaven. And I started working on this in 1999. So this is coming to you as a gift. In 10 years, some of you will be doing graduate work, you might be assistant professors, you might be teaching, and this really is the place where you would want to work. So think about this talk as if it's an invitation to start thinking about it. You might, there are 21 Indian institutions now part of this program, out of 260 or so institutions which have joined around the world. So you'll have ample choice to be in India and participate, or go outside and participate. And
we are live, sir.
Look, perfectly timed. Excellent. So, thank you very much for inviting me to give this talk. I always like to come to such venues and talk to people outside the field because they need to know why we as scientists get excited about it. So the first thing I'm going to tell you is that I have called this a super God particle. How many of you know what God particle is? God particle, yes. The Higgs boson was called the God particle. And the reason why it was called the God particle was because it imparts mass to everything that we see around us. That is the claim, right? And we are going to look at this from that perspective, and I'm going to tell you why, in my opinion, this is a super God particle, okay? So that's the background for that. And the glue comes from a word that says gluons bind all the quarks inside the proton. Does everyone know this? You can just say nod yes or no. No, you haven't heard. Okay, that's good to know. That's how I'm going to pitch it. So if you look inside the proton, everyone knows protons, I assume, right? And neutrons. But they were, until about 1960s, we didn't know that they had internal structure. Since then, we know that they have internal structure. So they're not fundamental particles anymore. But they are the building blocks of the universe that we see around us. Everything that you see. Not just on the earth, but in the skies, all the stars, all the galaxies, everything that we know about the visible universe is made up of protons and neutrons. And now we know for the last 50 years that those protons are made up of quarks, typically 3 of them that bind, but they are bound together very strongly by a particle called a gluon. And that is the carrier of the nuclear force inside the proton. So we are going to talk about that today. Throughout everything I say, that would be the one that I'll be talking about, okay? So that's the idea. That's the introduction. So the quest for the fundamental structure of matter, the curiosity as to what is the most fundamental thing, has been around for a long time. Many centuries. So here is matter as we see it, and I have taken as an example water droplet. And that water droplet, we know that it is made up of molecules of water that we know in chemistry and physics, early physics, you know it's H2O. Now that H2O is an atomic system, molecular formed of those atoms of hydrogen and oxygen. If you look at the atom of one of them, then any atom has a nucleus in the center and electrons around them. We know this is the atomic structure, beautiful system that we know for about 100 years. Then people did scattering experiments and figured out that at the center of them is this very hard object, which we call the nucleus, and it is made up of two things, protons and neutrons. If you look inside the protons, as I mentioned to you, in the 1960s we discovered that the proton is made up of two U quarks and a D quark. Up quarks and down quarks. I'll come back to that, but they are just take that as a thing. There are two quarks here of the same kind and a D quark which is different. But you see that there are colors are different. So no two quarks of identical nature can be working with each other. There has to be some difference. Okay? So that's why I have called them color, and you will see that actually this is real. We call them we know that they have some different type of charge. Electricity has positive and negative, right? Electrons and protons or positrons are negative and positive particles. Here they also have something, and I will talk to you about that, but in addition to that, they have a different kind of charge. And we call them the color charge. And there are three colors. And why do we call them colors? Because there were three types of things. Like in electricity, we have positive and negative. In strong interactions inside the proton, there are three types of charges. And we knew, artists knew that three colors make a colorless object. You can mix the three colors, fundamental colors, and make a white color or black color, make it colorless. So they just took the analogy and said, hey, this seems to fit. So that's why they are colored. Okay? There is no actual red, there is no actual yellow color, but they have something that behaves exactly like the color. Like three things mixed together becomes a colorless object. Proton is a colorless object. Yeah? Every time you see anything that is visible in nature to our eyes has to be colorless. Remember that point as well. So if we now know that the protons are made up of quarks and they're bound together by something called gluons, which is sitting behind this right here. You see this wiggly object, and that's where the gluon is. That is binding the quarks together. All right, so how do we know this? To know that, I want you to understand one concept that is called resolution. Now, these days, because you all have a digital phone, you know what, or nice television at home, you know what resolution is. Most of you have an intuition for it. Here is what resolution is. Here, I'm showing you something here, and I'm going to try to ask you, can you identify this object? Okay? And in this picture, the smallest square is of this kind, this size here, and that is what we will call the resolution. And as I improve the resolution, in your mind, you'll start making a correlation between what you see and what that object is. All right? So now, I have this as a resolution. Can you identify what this object is? You're too bright. Okay, you're right. You're absolutely correct. But what I want to show you is now I am showing you resolution increases. You see that? It becomes clearer, then it becomes even better, and you start seeing the smaller and smaller objects. You see another one, and now you see its Statue of Liberty very clearly, right? What improved from that first picture that I showed you to the next one is what we call resolution. So the smallest pixel of information is much smaller than this. You can't even see that small size, the granularity. That is what is called high resolution. That is exactly what we do in experiments. So here we have a microscope. Most of you in high school must have used it at least once. If not, you would probably have a home kit where you can actually start seeing things from your dirt in the background, yeah? And you can see that. So what happens here? In a microscope, you have an object and light falls on it. Light has a wavelength, yes? And that wavelength is so small that it can then hit that object and gets reflected. And then there are some features of the microscope that tell you how to see that, what to see, right? What comes out. But it's the light that comes from outside around you that gets reflected into the scope. That's how you see it. And that wavelength is the visible wavelength is from 380 to 740 nanometers. Now that allows you to look at things which are 200 nanometers wide. Typically that's what you can see with such a microscope. When you go to an electron microscope, where now you use an electron beam, and it turns out that electron beam, when you see it, that can be, because of the laws of quantum mechanics, the electron can be a wave or a particle. Okay, it's known for about 100 years now that such a thing exists. You don't need to know more than that, but you need to know one thing, that a wave of that electron with that energy is the one that is being reflected exactly like in the first case, there was a light wave. You don't have to know exactly, it's the same principle. It's the electron wave that is coming back. And that's what we do with the resolution. That once you have that, your resolution is improved. And we as particle physicists or nuclear physicists go to even higher energy. So now I have a very, very high energy accelerator. This can be 3 miles long, 5 kilometers long. Yeah? And then at that high momentum, that high in energy of the electron, the wavelength is much, much smaller. So that means I can now look at even smaller objects. Why do I need it? Because the proton size is so small that light cannot see it. I have this, suppose this is the size of the proton, and I have a wavelength of light that comes like this. I'm going to easily miss this, right? Wavelength comes through and missed it. But if I have a wavelength that is like this, small, then this has a high probability of reflection. So I need very, very small wavelength, very, very small wavelength to look at smaller objects. The smaller the object I want, the smaller the wavelength I want. And that means the wavelength has to be, the energy has to be much larger. Okay? So that's what we do. We have the electron accelerator, high energy electron or proton, any particle, comes through, hits that target, and then things come out flying, and we build detectors. That can be the size of this room. Because the energies are high, the exhaust of that collision can also be very large. So that can happen here. So the rule that I want you to remember now, that I've told you already, you have understood it hopefully, is that the wavelength with which you are seeing things, yes, has to be inversely proportional to the momentum, the energy of the incoming particle. That's all you need to know. Let's go to the next step. So what do we know? This we have done, as we meaning humankind, over the last 50, 70 years, using larger and larger energy experiments. We have done this, and what we have discovered is that all the cells are made up of molecules. Molecules are made up of nuclei. In the center, atoms, then nuclei in the center, protons, and then we have discovered, as I said to you, quarks. And they're bound together by something called gluons. There are 6 types of quarks that we know for sure. There is no 7th type right now. 6 types of quarks. Each one of them has 3 colors. But most of the world that you and I see each around is made up of these 2 first, up and down. So the proton is called 2 ups and 1 down. Yes, neutron is 2 downs and 1 up. So the U and D quarks make up everything that we see. You have to do something specific. You have to go to a high energy in a collider to create heavier quarks. Normally they don't exist. If you want to study it, you come to me, I know how to create them. Yes, and then we study them one individually. So this is the frontier of our knowledge so far. So there are 6 types of quarks which are sitting here. I told you each one of them will have 3 colors. There are neutrinos. I'm sure you've heard talks about that. And then there are electron, muon, and tauon, a charged sister or brother of the neutrino family. Okay, so that's the system. Now, these are the particles which interact. Those are the forces. The first one is called the gluon, which is what going to be our main topic today, but there are others. The photon is the carrier of electromagnetic energy. So the light that you see there is a photon of a particular wavelength. To change the wavelength, you change the color. Yes? Then there is the heavy particle W and Z, which are the heavy sisters of the massless photon. The photon has no mass. The gluon has no mass. But these two unusually have mass, and so in 2012 we discovered the Higgs particle, which I told you, introduced you as the quark particle that creates mass for everything that we see, including these quarks. Yeah? All right. So we'll focus today on the gluon. So what distinguishes the QCD? I told you there are three colors, and as was mentioned, because of those colors, the interaction between them is called quantum chromodynamics. Chromo means color, yeah, as against quantum electrodynamics. So what is the big difference between them? What is the most fundamental difference? The fundamental difference is that the gluons and photons, and the three parts, they are the carriers. The gluons carry color. They themselves are charged in that strong interaction. Yes? They are already charged. The photons, however, are not charged. There is no charge on it, right? Like positron, proton, they have positive and negative charges, but the photons are chargeless. And in this physics, these particles can only interact if the other particle is charged. The charges attract or repulse each other, right? So there has to be a charge to interact. Remember that. Gluons carry color charge. That means gluons can interact with other gluons, because one could be a red gluon and one could be a blue gluon, and they know how to interact. They know that the charge is different. Correct? Photons have no charge. Means there is no chance a photon will interact with another photon. Photon will interact with the electron, it will interact with the proton. Anything that has electrical charge, it can interact. That is the big difference. And this is going to create the entire mystery, entire difficulty that we so far have engaged or faced in lack of knowledge of the gluon, or QCD, quantum chromodynamics. And I'll show you how and why. So if you take those two rules that only charged particles can interact with each other, here is what the picture comes out to be. You take a gluon, that's the curly line here, it can interact with quarks and antiquarks. That means it can split into quarks and antiquark, or it can split into any charged particle like that. But because it itself carries color, it can split into two gluons. That means it can interact with another glue and form a third glue. It can also have these four particles. One gluon comes in, the other, they interact and result in four gluons. Yes? That can happen. That can never happen in a normal electricity. The photon can split into electron-positron pair, as shown like that, or antiquark and quark pair. However, there is no chance that the photon will interact, have a diagram that looks like a triangle like this here. There is no chance. No chance here. And this creates all the mystery and richness of QCD. And this will appear again and again in my talk. So just remember, photon-photon interaction is forbidden, or photon splitting into two photons is forbidden, but gluon can always split into two gluons or three gluons. Yes? That's the fundamental thing. Now I'm going to tell you a little bit about the method we are going to use to look inside the proton. So what I'm calling a deep inelastic scattering, DIS. Deep meaning going deep inside something. So I want to go inside the proton, fly into the proton. Inelastic scattering. In the introductory courses in physics, you have two types of collisions, elastic and inelastic collision. And you probably have seen calculated things, right, for two cars colliding elastically and inelastically. Inelastic is a the one in which the cars get mangled up, because the energy of the initial energy of this collision gets pushed into the metal parts of the body of the car, and they get mangled up. If it is a glazing collision, that's called the elastic collision, there is not much that happens to the car, because the energy of the initial state, after state is the same. So not much happened to mangle the metal part of the car. Yeah? So we are going to do the inelastic scattering because we want to see inside the proton. Feynman, who was a great physicist in the 60s and 70s, he wrote that if you scattering of protons on protons, like you want to understand the structure of the proton, at that time we were trying to understand it, we didn't know much about it at all. Is like, he said, we will colliding protons on proton is two garbage bags, or he called it Swiss watches. If you break them, what will you know? You not know the structure of it, you know what's inside. You don't know how it works. You just know what it's in there, you know, these springs and all these detailed things. But we want to do something different. We want to go beyond that idea. So I think that this experiment is a bad one. And I have an analogy which I use, which is slightly different. If you are asked to study the internal structure of a watermelon, you can do two kinds of experiments. You can do that. Come on. Oh, it's just slow. So you can do this. You can take two watermelons and collide them with great energy. And what you get is this mess. That experiment tells you that the inside of the watermelon is the red, the sweet, the meat of it, and then the seeds. And then there is a white cover to it. That's all you can tell me, definitively, as a scientist, right, during experiment. But if I ask you, I don't want that. I know already that. Now tell me how the seeds were arranged inside the watermelon. That's not the right experiment to do. What do we need to do? We need to do that. We need to cut the watermelon with a knife. With a knife. Because then, when you collide the knife with the watermelon, the knife doesn't break. And you have full control over how you will cut the watermelon. And you will see the seeds and the distribution like that. That is deep inelastic scattering. Okay? I'm going to take the proton and hit it with the electron. Electron has no structure. As far as we know, we have never seen the internal structure. It's still called the point particle or the muon. It's a point particle. It has no structure. With respect to the watermelon or the proton, this is beautiful. I can control the cutting of that proton the way I want. Yeah? So that's what we are going to do in the future. And here is the diagram for it, what we call Feynman diagram. You see that as a knife is coming, the electron is coming from here. It exchanges a photon, a high energy photon, because you remember you want to shine something and look back, right? So that photon has to have a wavelength which is smaller than the size of the proton. Remember, all these things have said that, right? They have to have a size such that, wavelength such that it is smaller than the size of the proton. If not, you're going to miss it. So you want to go inside and then break this thing up and get shines back from the quarks. Yes? And then those shines, whatever comes out, I measure with a detector. So I have the watermelon, the knife, proton or neutron or the nucleus, doesn't matter, whatever it is we want to study. And on this side you see the remnants. The q squared, the momentum is the exchange between these two, has to be large enough to go inside because the wavelength has to be small. Remember, 1 over p. And then you get that slide. Then you can tell me how the distribution was. And that's what we want to do in the future with the proton and the nuclei. Never been done that way. So now let's look at the mischievous God particle, super God particle. Why do I call it mischievous and why do I call it super God? So let's take an example. I told you that the Higgs boson was called the God particle because it imparted mass to every visible thing that we see in nature, including the quarks. Yes? And quarks make up everything that we see, protons, neutrons, and everything, right? And then suddenly you ask, what is the mass of the quark? The first question, right? Because the mass is being talked about here. And what is the mass of the proton? So here, if you take the three quarks, the U, and D, and you add up the mass of those, it comes out to be about 2 × 10⁻⁻26 grams. But the mass of the proton, which has no more quarks, it has only gluons binding them, now it is 100 times larger than that. But I told you the gluons were massless. There was no mass to the gluons. The quarks only carry 3% or 1% of the total mass. But the massless gluons are creating proton, and the neutron is the building block of the entire universe, which means I'm telling you that 99% of the mass of the universe that you see comes from gluons. And how does that come about? We don't quite understand it yet. But we know for sure it does. Yes? And the only simple way of understanding is these quarks and gluons are interacting with each other. It's the soup of quarks and gluons inside the proton. Those gluons are not static. They carry energy. That energy is being converted by Einstein's equation E is equal to mc squared into the remaining mass of the universe. And we still don't understand it. The simplistic way of looking at it, but we need to understand it. Yeah? So that's why I call it a super God particle, because it contributes to 99% of the remaining mass of the proton. Because if you just take simply mathematically, it's like saying 1 + 1 + 1 is equal to 300. Right? We know it's obviously wrong, and we need to understand where this 2797 comes from. Okay, so now, another problem we have. About 100 years have passed from the discovery of atom and the proton. We know the atomic structure so well, now the electronic structure and the atom, all this picture is so beautifully known, that the accuracy with which we can now make these measurements of the electronic transitions is 1 second in 220 million years. We have built clocks, yes? They are giving us that accuracy, and they're all based on electronic structure, the time with which the electron goes around, etc., etc. If I ask you, if I were to build a clock using our knowledge of the glue, it would be 20 minutes in an hour. That means you and I can measure by your body experience better time than that, right? It's 20 minutes to an hour. That's the bad uncertainty. That's the bad knowledge we have. That's how less we know about the internal structure of the proton. And I'm going to show you a picture. Now, we learned about gravity, and there's something about spin I want to tell you. Proton also has a property called spin. It is spin half in some units. You don't need to know why, but it is very fixed. It's very fixed. If you have, God forbid, not too often, have you gone to take an MRI of yourselves? Yeah, in medical, it uses that property of spin half. You put the proton in the accelerator and accelerate, it's exactly half. We know how to build a magnet to accelerate the proton. It is always 1/2. It's a fixed thing of nature. But I told you it's made up of quarks and gluons. So you need to understand how these quarks and gluon interactions, at 99% of the hidden mass, the same interactions are exactly giving the proton its spin half. No matter what energy you measure it in an atomic physics lab or condensed matter physics lab or a particle physics accelerator at CERN, the spin of the proton remains the same, half. And amazingly enough, all the internal dynamics that is affected by these energies from atomic physics to particle physics, all that dynamics is taken care of inside. Always, spin comes out to be half. Why? We don't know. But here, the analogy is, in the high schools, you learn about gravity, or colleges, undergraduate, you know about gravity, magnetic fields, orbital motion of tops, yes? That's all classical physics, yes? And then, I show you this, which is a spinning top, and it is not very easy to explain what is going on. Although you know all components of it, the gravity, the mechanics of rotation, etc. And you see what happens. This is a recording that I did in my office. Here is a plastic top with a little bit of an aluminum ring to it. There are some magnets in that black box. I'm not hiding anything here. No magic. Yeah, it's levitating. Isn't it fun? Yeah, look at that. So this is a levitating top. Although every component of the knowledge of physics, undergraduate physics, classical physics you have, try explaining that. It's not easy. Okay? And at the end of the talk, I don't have time to go into the detail now, but at the end of the talk, we can have a nice discussion about it. Yeah? So the point I wanted to make here only is that even if we know all the simple parts of it, when spin comes into picture, as I was talking about proton spin, somehow magically it knows to get to that one particle number, 1/2. Things that we know about physics break down. And that's what happened to my early experiment at CERN, and I'm going to show you something about that. So spin is an interesting property. We know that spin of the proton is half. It is made up of 2 quarks and a U quark, 2 U quarks and 1 D quark. Each one of those quarks has a spin half. That also we know. I didn't mention it. I should have mentioned it. Each one of them is spin half. So 3 quarks making up this proton. In the 1970s, we thought this was a simple system. I could explain spin half of the proton to be spin half, and spin half, some combination. So it's one is spin half, the other one is pointing to the other direction. So that's minus spin half. And then the third one will be 1/2. So the sum of it is 1/2. Yeah? So this is a simple system. You can actually take this model and calculate properties of the proton, and they work out to be, except for the spin. Magnetic movement and other particles, the size, people had done that. Works out. Except that we went in and did the experiment at CERN. What did we do? We took the proton, we put it in a magnetic field and aligned it this way. Now the spin of the proton being this way means that the 2 quarks, at least 2 quarks have to be spinning this way and 1 spinning that way, right? I told you this simple, +half, minus 1/2. And then I shine light on it, meaning electron light, this very high energy light, it's virtual light, very high energy, to look inside, and I could see the quarks. That was not the surprise. But now, for the first time, the quarks were aligned or misaligned with the spin of the photon itself. Yes? And I could see the correlation between these two. And I could do another experiment in which I flipped the proton spin to the other direction, and I repeated the experiment, yes? And now I see a different one. You see, this proton spin is going that way, and now I have to have 2 quarks spinning that way and 1 might that way. But this is a controlled experiment. I know exactly what to expect. If the proton spin was given exactly as this model told you, the 3 quarks give you, the difference between them was exactly known. And that has to be this part here. It's 2/3 the probability of hitting the quark here, and this is 1/3 the probability of hitting a quark here, because they are the ones that are misaligned, which will interact with the quark, with the photon. So the difference between them was exactly known. We knew exactly what to expect. What we found was that it was no correlation at all. No matter what direction we did this, the answer was the same. So the difference was always 0. Which meant that the quarks did not carry any spin at all. So now we are in a quandary. We now know 2 things about the proton. That the mass does not come from the quarks, and now the spin doesn't come from the quarks. It was called the spin crisis. New York Times, London Times, they all called it the spin crisis, because this was a crisis to the people who had built this model. So the spin is not easy to explain. That was the message that we wanted to give you. Over the years, we have measured this very precisely. Now we know that the spin half is coming partly from the quarks In the last 15 years, I have tried to measure the spin of the gluons. How many times have the gluons that I already introduced to you is aligned with the proton? And that is what we call the evolution of our understanding of the simple model of proton has moved into something which is much, much more complicated. Those three quarks, they are not stationary, they're moving. Why should they be stationary? Why did I even first think about it, right? They had some energy, that means they must be moving. If they had energy, they should be radiating also. They might interacting with the gluons. So the complex picture of the proton emerges that those three quarks, which are these three principal ones, which we sometimes call valence quarks, they're still there, but there is a lot of gluons in there, and there is motion there, and all of this somehow comes up with the exact property of mass and proton and the spin. Yeah, and that's what the future investigation is. Just to give you a picture, we have measured this to be, we are looking for half. We have measured the quark spin to be about 0.12 and measured the gluon spin to be about 0.15. So the half of the spin of the quarks, half of the spin of the proton is approximately coming from these alignments from quarks and gluons. The remaining part comes from the motion of the quarks and gluons. How do we go inside the proton and look at the motion of the quarks and gluons? That's something, this is 10 to the minus 15 in dimension, centimeters. And now I'm asking you to go inside and actually decipher the rotation and the motion of the quarks. That's for the future, the quarks orbital motion and the gluons orbital motion. And the proposal that we are making now will actually measure this in 10 years. So here is the part of the construction of the project. What we want to do is to build two rings, one with the proton, one with the electron, hit them, each other, against each other, with controlled spins, because remember we wanted spin as well, correlations, and we see what comes out. So it has to be deep inelastic. We also want to study the nuclei as a target to make sure that everything is fitting, and so that's what we will do. Now, again the same experiment. Here, who the bright person here was said, oh, that's Statue of Liberty, even before I went to the next one. Now I'm not going to show you that. Now, because we don't know anything about the transverse dimension inside the proton, how these things are distributed. Remember, spin means what? It is moving, right? Initially, I was talking about only spin alignments of these quarks. They don't have to be moving, but once the movement comes in, there has to be a three-dimensional object. A three-dimensional object means if I look at it from the top in this cartoon or this animation, there should be a distribution in 2 dimensions, yes? Now I'm going to respect the proton as it should be in complete 3 dimensions. But we don't know anything about it, which means that you cannot have the intuition that this person had before I clicked. So when you don't have that intuition, then we go into a very different problem. Okay, I will come to that. So far we know by looking at this what a human being is. You look at this, this is a human being. That's what we call proton so far. Now we have to go and look at the 3 dimensions, and that's really the 3 dimension. That's the real thing that we want to study going forward. The 3-dimensional structure of the proton, which we have no intuition because we have never measured it. So I really don't know how the proton, if the proton is coming at you like this, I just know the radius. What's inside? How are things distributed in that direction? You have no idea. If that is the case, then you cannot build the intuition. You cannot judge this. Now try to judge this. Go, keep. If you know it, keep it quiet. Otherwise, you'll kill my second animation too. Artist in the picture, in the room? No? You know? Okay, you came to, okay. All right. So 2 people know. All right. So, but for most of the people like us, mere mortals, we need to have high resolution. These are gods, they just know. All right. So here's the answer, right? Because we don't know anything about the landscape of transverse objects inside the proton or transverse motion, we need to really measure it. That means I have to improve the resolution step by step and go up. Can you see now? Except for those 2? Can you see now? No. Because you have no roadmap, you have no intuition, no knowledge. And that's what is exciting about science, right? You have to go up and up and up in resolution. Do you know this? Yeah? So now you know, right? But I couldn't judge it because I have no idea. Because Dali has this twisted mind. And with that twisted mind, he creates these absolutely fantastic objects, which are not common. They are not intuitive, which means that we have a problem. And for that reason, we cannot extrapolate from our current knowledge of physics as to how a proton looks like in 3 dimensions. We actually have to go and measure it directly. And that's what we will do next. So I told you, and this is only 1 or 2 slightly more technical, but it's easy now that I've seen the nods, so I know you will get it. So here is the proton. I've tried to get it in 3 dimensions. And there is a quark in there. It has the property of movement in this direction, is the direction of the proton's movement. And all I'm asking you to imagine, in the 3 dimension, I have the y and x, and it has a transverse momentum. Because if the proton is like this size, transversely, there is no reason the the quark sits there quietly. It will move and it will come back and move and come back. It will use its all freedom to go to the edge and come back, right? And that's what, all I'm asking you to imagine is this. Think about a proton. Inside there are quarks, they have the energy because of the glue, they're excited, they can go, but they have to respect the boundary somehow. We don't understand that why, but there is a boundary. That means the proton doesn't disintegrate by itself, right? It sits there because otherwise we wouldn't exist. All our protons, we are bound, all nuclei are bound. So if I want to see the motion of it, here is the experiment I want to do. So here is the assumption. The quark is moving like this. You see the small arrows here? It has an orbital angular momentum and in that direction, yes? And then I hit it with the electron, the photon exchanges, but at the time of the hitting, the quark was moving from the left to right in this picture. And it has energy now that I gave it. It starts moving in that direction, and it comes to the end of the proton and knows, oh, I need to go, I need to overcome this. But it cannot, ideally. But I've given it so much energy that it will break the proton. Deep inelastic, remember, deep inelastic. But when it goes out, I already told you, it also cannot be a colored object. Quark is a colored object. So in a hurry, it looks around the proton and say, hey, anticolor, any particle with an anticolor, I need a wife. And then they both come out as a couple. And that couple in our language is called a pion. Pions or kaons are particles that we have seen. There are 2 quark objects, 1 quark and 1 antiquark. Always come out that way. So we have solved all the problems of the constraints. These pion I can measure in my experiment. It can be a pi plus, pi minus, etc., etc. But what did I know? By the fact that the pion went in that direction, I knew that the quark was moving in that direction. Right? If the quark is moving in that direction and I hit it, pion is going to go there. If the quark was moving in that direction, if I hit it, quark is going to go there. Yes? That's just intuition, right? It's momentum conservation, but it's intuition too. So that's how we measure these things. And we have measured it, and we will measure it in the future as well. So that tells us directly something about that. There is another thing, and then I will eventually make these pictures. When I take the proton and it is polarized in some, polarized meaning it has spin oriented in some direction, amazingly enough, our current knowledge of U quark tells us that the distribution might look like this. This is an MRI of a proton. MRI of a proton. We will be able to see this in 10 years. This is just a simulation, but that's the resolution we were going to get. And now really see the U quark was that way. I'll show you another picture in which we have done simulations of the D quark, which is coming up next. So now I told you how to measure the left-right movement, but I also want to know the position. And that position is slightly different. Now, if I have a 3-dimensional object, let's say I have a glass bowl, yeah, and there's water in it, and there are 3 ping pong balls. 3 ping pong balls are my quarks, the glass bowl is the proton, and the water inside is the glue. And I churn it like that, and that's my initial system. So everything is moving around inside. Now I ask you, hey, tell me, how fast is that ping pong ball moving? You will not take a cricket bat and hit it like a deep inelastic scattering and break the proton, right? Break the glass. That will destroy the whole system. You don't want to do that. You want to take instead a soft table tennis ping pong paddle, go in softly, see how much pressure you see here, how much pressure you see there, but don't break the proton. I told you all the years I worked on increasing the energy of the electron beam so that I can go inside and see, and now I'm telling you, hey, by the way, I also want to see in such events, the proton does not need to break. I want to see the internal dynamics of the quarks by softly going in. It turns out that in 2000, in one of my other experiments, we discovered that about 6% of the time, this actually happens. So 6% of the time, the photon, very energetic photon, goes inside the proton, excites a quark, and leaves the proton. So what we see outside is an excited de-excitation of that quark that comes as a photon and an intact proton at the end. Who expected that? We didn't. In fact, we were sure we had made a mistake in the 3 years we tried to struggle. And then theorists like Pranav told us, or mathematical theorists, they told us that, hey, you can get 6% of the time this kind of a reaction. And then we looked for it and we found it. Because I don't want to break the proton, I call it a non-violent collision. Before that, all violent and deep inelastic, right? I want to call it a non-violent collision or a Gandhian collision for our audience. Yeah? And what happens in there? So here is the proton, and I hit it with that photon, electrons comes in, scatters, the photon goes in, does the excitement, leaves a photon out, I measure that, but I also measure the intact proton in the final state. And the inside, really what's going on is this, that the quark gets excited by that photon, it de-excites, falls back into the proton. So you have the intact proton again, no problem. Sometimes the other type of interaction happens, as shown here. Instead of a quark in the initial state, there is a gluon that gets excited by the energy that you add to the proton. And then you have a slightly more complicated, but what we see a vector meson, is a heavier brother of the photon that comes out. Okay? So this tells you about the gluon, this tells you about the quark. Positions now. Yeah? So then, I told you the U quark distribution in a polarized spin proton, the D quark looks like that. And now the position distribution by these non-violent collisions, we have done simulations as well, they look like that, unpolarized and polarized. You have a spin, so all I'm telling you is that we are going to create a tool in which we are going to see such things. What we are going to see is not necessarily this. In fact, I would be delighted to see something completely different, because that's when we will learn something new. This is something based on what we know about the physics of inside. And the excitement happens most often when you don't see what we expected. Something similar to what happened to the proton spin. Remember? We thought that the quark spins were contributing to the entire spin. We found nothing. We found 20%. Yeah? So we want to see excitement here. We want to see the surprises. So in summary, I've told you that this is what I intended to do. And now I'm going to show you, say, that I'm going to take an MRI from watermelon. That's really what I want to do without breaking it. I don't know why internet has MRIs of watermelons, but it helps me make this case very easily, right? Who has the time to do that? But it sort of saved me a wonderful. Anyway, last point. I told you to imagine, to think about E is equal to mc square. I'm going to call Einstein one more time in the room and recall that there is when you take an object to a high energy, high velocity, then something changes. Everyone heard Lorentz contraction, contraction in length, and dilation in time, time dilation. You probably have heard talks where twins went, one of the twins went out and came back. One was younger than the other. That's because of time dilation. That's time dilation. But when it goes, the length of the object also decreases, yeah, in the direction of the motion. So those two things I want you to remember. on this cartoon. So I have a proton which is sitting in my lab. Here's my cartoon, 3 quarks. There is some glue there, I'm not showing you that, but just to make the point. And the time is going in that direction, okay? And what happens to that room temperature proton? The quarks are emitting these gluons, those gluons come back into the quark, and you know, they are just happily bubbling, going out, coming back in. And then I do an experiment, and this is my blue dot, is my experiment. I take a picture of that. And that picture tells me how many quarks and how many gluons are there in the proton. And that's this one here. I can count 3 quarks and about 6 gluons. Now, if I do the next step, I accelerate the proton. Now I have the symbolically accelerated proton, which is Lorentz contracted. And now what happened is these gluons are time dilated. They're long. They live longer. If they're living longer, they can emit into 2 other gluons much more often. Remember, gluons can split into 2 gluons. Photons could not do that in the beginning of the lecture. Remember that? That cannot be done here. That means that now you suddenly get an increase in the number of gluons that you can measure. And that's all happening. That's exactly what is happening inside the proton. You have written from this Nobel Prize winning lecture by Frank Wilczek that you take a glue, splits into 2, 2 becomes 4, 4 becomes 8, 8 becomes 12, 16, and this can go, this can blow up. So he says that a self-catalyzing enhancement that leads to a runaway growth, a small color charge in isolation can become a big color thundercloud. That is telling us that it can go to infinity. Physicists don't like infinities. That never happens. Yes, it shouldn't happen because in our world, we don't see any infinities, right? Protons are stable. This is telling you something else. So what is the difference? The difference is that protons are bound inside the proton. The gluons are bound inside the proton. And as you go up in density of these gluons, they're getting crowded like a train in Mumbai or in Bangalore. And then they are going to start hitting each other. And that hits are going to create mergers. That means as you start growing in numbers, you're also going to see mergers of these gluons. You see so the number is going to somewhere stabilize. The increasing tendency and the decreasing tendency are going to be equal at some point. And amazingly enough, QCD as we know it today predicts such a saturated state of matter. Remember, it's a completely gluonic matter, no quarks involved. Amazing, we have never seen such like things. So this is an amazing state of matter. It has some fantastic properties like energy densities are 100 to 1,000 times larger than the core of a neutron star. That's the calculation that tells us. Whether it is true or not, we don't know. But something of that kind we want to see in this future collider. It is called a saturated state of gluon called color glass condensate. Yeah? It is a fascinating new state of matter that is predicted by doing this kind of a thing. So I think, am I going late? Okay, yeah, I have few, just concluding. So we have done beautiful physics over the last 50 years, looked at various Nobel Prizes that have been come to protons. Now we are going to do not only this proton, but control its spin and repeat those experiments. We couldn't do them in the last part. And now we understand QCD well, and we'll measure that again. And in addition, we'll do this with nuclei, where all these nuclei, when you accelerate them, they become extremely dense. So we enhance the gluon density that we want to see and see if there really exists such a saturated state of matter. So realization is going to happen this way. If you go above Brookhaven National Lab in a helicopter, or if you are landing at JF Kennedy Airport, you will see this lab on the right-hand side. Yeah. So here is the RHIC, the relativistic heavy ion collider, which we are going to convert into an electron ion collider. We'll take one ring out. Currently it collides protons and protons, or nuclei are nuclei, like the watermelons on watermelons. I'm going to take one of those rings out and put an electron ring instead, and convert the same complex into an electron ion collider complex. So it's going to look like that. Injection is the same, and then this red line here is the electron beam, and then it will collide with nuclei and protons under controlled conditions to understand the spin as well as these heavy gluonic object that we will try to see. And here is another view of this. The electron will come here, the hadron will come from there, and there are two places where you can do these collisions. Let me skip. So this is what we are trying to understand. How much of the proton's property come from the alignment of the glue, the alignment of the quark, but now in addition to that, what is the role of the orbital angular momentum? But remember, not just that, that motion is also intimately connected to the remaining 98% of the mass of the proton. So it better come out to be right. Yes? That angular momentum should result in the mass or get the mass, and that, so it has to be, you don't have too many free things there. And we physicists like, experimentalists especially, we like this kind of a constrained system because we can check one independently and go in another lab and do that, and they better come out to be right. That's the beautiful part of science. So knowledge of our science has resulted in this simulation. So I'm going to show you one more simulation here. So what is shown here again, resolution is this block here, yes? And so this is the first picture is in a bad resolution, okay? So I'm going to start that, and you see inside of the proton doesn't look anything interesting. This is at Q squared of 1 GeV, okay? That's a very small number. Nothing really happens. You can see some changes in that resolution, yes? Now, if I go somewhere, I'm scanning the proton at different positions inside the proton, different momenta inside the proton. Now I'm going to increase the resolution. Remember the large number, 100 or something like that. That means that goes into denominator. The wavelength changes. Suddenly you start seeing these beautiful pictures, which are high resolution pictures of that. And you can see the gluon taking charge, and the quarks come about when you look at it from a high momentum point of view. You see this? As soon as you start coming into this region, you see the picture of the proton as classically we thought, made up of 3 quarks and lots of glue around it, yes? But this is only I know from what we have known so far. I don't know how to put a spin on it. Figuratively, I am literally, right? I don't know how to put a spin. If I tell you I want to measure the orbital motion, I will measure it in 10 years and then put that into simulation. Currently, this is what our knowledge is. Yeah? So this is why we want to do it. Here is the science summary. You can explore. This is a live link. You can go there. There are lots of simulations that I just showed you. Look at it and try to understand deeper into what I have already told you. So the summary is, the gluons, which I call supergluon particles, they bind us all, and they're responsible for 98-99% of the mass of the universe. And we don't understand it. That's something that means it doesn't make me unhappy. It just makes me happy because I have job. I'm not jobless anymore, right? The spin is the same thing. As scientists, you should be happy when you have something that is not understood mathematically in classical physics. We need something that we need to understand. And it is an experiment-driven field because those glue-glue interactions, they're extremely difficult to calculate. Why? Because you have one glue, has some energy, it can split into 2, goes into 4 can be going into 8, and you don't know where to stop because there always will be an energy which is half the existing state and still keep on going. Yes? So that part makes it very difficult for theorists to calculate. The only way to go forward is to do that experiment, give them the number, and say, explain this. Yes? That's what is going on. So the object is a significant momentum. We're going to start construction in a year and a half, about 2025, and the first collisions are expected in 2031 to 32. And as I mentioned to you earlier, it's an exciting time. Join us. You can go to that webpage as well to understand a little bit more technically. And then this is really a machine for the young scientists in this audience. If you are interested in this, go to your nearest university. It doesn't have to be at Long Island or something. Not yet. You should come to Stony Brook. I would love to hear you. But you don't have to do that. There are 21 institutions in India who are part of this. All IITs are getting involved, IIC. I'm trying to entice everyone who is interested in this science to get involved because these are really unknown things that we need to know. Thank you very much.
Thank you very much for this wonderful talk. We were actually glued to it.
I like that.
So now the floor is open for questions.
Yes.
And the mic will come to you, so talk into the mic. Okay.
Any questions?
How would we measure the interactions of an electron with a gluon, since the gluon doesn't really mediate the electromagnetic force, right?
Very bright. So what happens is the following. You're absolutely correct. There's no direct interaction. But what happens is something, next, are you a physicist? Oh, you don't need to know. Okay. So the electron emits this photon, remember? The photon can emit quark and antiquark pair. And then that interacts with the gluon. Because quark and antiquark are charged, color charged, gluon is color charged. So it is called, in technical terms, next to leading order correction or next to leading interaction. It is not like the photon emitted by the electron hits a charged particle directly. Yeah? But you're absolutely on the correct phase. So it has one more step behind. Because the photon then splits into quark antiquark, you can do that.
More questions?
Hello. So,
There was a hand here. Yeah.
yeah, so like you told that proton is made of 3 quarks, that we know. But
And a lot of gluons.
yeah, so yeah, basically that was my question. So we currently don't have any quantification how many gluons are there?
I told you, you can't.
Okay.
You cannot have a fixed number on it. What you can have is the total momentum of the proton and the total contribution to the linear momentum of the proton that comes from the gluons. We know from experiments that we did at DAISY in Germany that about 50% of the linear momentum of the proton comes from the glue. But we don't know exactly the number. And we plot them as number density and it keeps on growing at the low momentum, but it's infinite. And this is what we are trying to solve actually. Once I see the saturation, I will tell you that answer to that number. That then I can calculate for you because that's a stable number. Until that happens, the gluon keeps on splitting. So I can't tell you a number. You get it?
Yeah.
Yeah.
Thank you.
Excuse me, sir.
There was a hand here, huh?
So you follow question to that question, sir.
Yeah.
So electron and proton are, you told that electron ring and the proton ring, we are including both and then interacting both of them and then interacting.
In the collider, you mean?
Yeah.
Yes.
Interacting that with the gluon, basically.
No. So the gluon exists inside the proton.
Yeah.
I want to see that proton.
Okay.
So a proton is just a vehicle.
Yeah.
People sitting inside are gluons and quarks. To see them, I bring them in opposite direction with the electron. As soon as the electron sees a proton coming in, it starts radiating photons, light. Those photons are the ones that then take over the job of going inside the proton, and because they can split into quark-antiquark pairs, they can directly see the gluons.
So electron is basically providing energy.
No, electron is providing the photon.
Photon, okay.
That then splits into quark-antiquark pair and looks at the glue. Yes? In the diagram, I can show you exactly the figure that I showed you before. Yeah, here. The electron is this one, the straight line going out here. It provides that photon. That splits into quark-antiquark pair and then looks inside here, either the glue or the quarks inside. Yes? That's what it is. This lady's time, waiting patiently.
Yes, sir. So I wanted to ask, sir, how does the types of quarks contribute to the charge of proton or no charge of neutron?
Right. So, U quark, let me go to the U quark is 2/3 charge. Yes? That's the unusual part of it. U quark has plus 2/3 charge. The D quark has minus 1/3 charge. So you have two U plus 1 D. That makes 2/3 plus 2/3 minus 1/3 is plus 1. That's my proton. And in the neutron, it is U DD plus 2Ds. And then you can do it yourself, you get 0. And that's how you get proton and a neutron. So, and protons and neutrons are the only thing that we see in nature. So what we see around us normally has mostly U and D quarks. But that doesn't mean that the gluons which are sitting inside the proton, remember the proton was called like that, but there is glue here, right? The glue can split into quark-antiquark pairs and come back together. This is happening continuously. And quantum mechanically, you can produce all quarks in there. And if you can zap them, if you can measure them before they come back and resolve into that glue, you will measure that. But because there is a mass hierarchy, it's more difficult to create heavier objects. Yeah? You need to have energy to create that, E is equal to mc squared. So, unless you do a collision at extremely high energy, you can hardly ever produce a top quark. Then comes the bottom. Then comes the charm. Then comes the strange. And then the two which are almost massless, U and D. Yeah? So there's always a small amount of extra, this new quarks in there, but it's very tiny amount. And we also try to measure that. The different types of gluons, there are already 3 types of each, the colors, and there are 8 types of gluons. You can make a combination. Yeah. There was not necessary for this talk, so I didn't use them, but yes, there are different types, yes. Because of the color combination, you can have these different types of quarks, yes.
Can I ask a simple question?
Yes.
So in that picture, when the gluon kind of multiplied and...
yes.
So what is the color? So there is no conservation of color or color charge?
It is internally there, absolutely. It has to be.
There
has to be there, absolutely.
Okay, okay.
Nothing I said here violates anything that we know of QCD so far.
Okay.
They're better not.
And still, but you had said at some point that if you want to measure something, it has to be colorless.
Correct.
Right?
So yes.
How do you hope to measure something like this?
So I didn't go into the measurement of this. So here is what. So I won't use the color properties at all. What happened? I told you that when I create this gluonic object called the color glass condensate, where is that? It's a saturated state, and it's very high energy, a high density. So what am I telling you? What should you take away from it? So here is the proton, or a nucleus, which is spherical otherwise, but I accelerate it, it has now become a pancake, a pizza, right? And I shine light on it. It has become a very high density object in the center there. So what happens when if you do this collision, one of the things that we see in normal collisions is that 2 jets come out. In the EP or EA, 2 jets come out back to back with the momentum conservation. If such a saturated state of affairs exists, then you will see only 1 jet come out. The other jet, which is extremely energetic, is stopped by the heavy mass of this. Heavy density of, not mass, heavy density of this. Yeah? So one signal we are looking for is the event that looks very odd. It looks like momentum conservation is not there. But we know it's not momentum conservation. It is the missing jet. The other type of experiment, which I think undergraduates will be very happy to see, everyone has done diffraction, right? Everyone knows diffraction. You have a beam of light, monochromatic light, and it sits at the edge. And you see these diffractive pattern of dark and black. But if you have a circle there, then what you see is maxima and minima that go like that, right? That's called a diffraction. It's a classic picture in introductory classical mixing. Here we are doing a diffraction of a nucleus. You have a very hard object which is created, and I'm shining light from that electron. It's exactly like that. And you expect to see the diffractive pattern in the final state on both sides in our collider detector. And we have seen the hints of that already because we have used proton on nucleus and seen proton is a different wavelength, but we see some broken diffractive pattern. But the electron is going to give us a beautiful, simple pattern because it's a very monochromatic light. Yeah, so those are the two things that I didn't mention, but thank you for asking. That's how we'll measure it. Nothing I said had a color correlation. Everything inside is colorless. Yeah, and I'm not breaking any law. Only the physical property of that material is exotic, making me call it the super glue, super God particle. Each one of them are three colors. I don't know that you can do a discrete. Yeah, discrete. Yeah, this is a picture I want to see what's happening. You can never see one gluon splitting into two because inside it's in color system, as she said, right? I mean, each one individual, it's a color system. They're colorless individually, but I don't know how to measure that. But the bulk property of the nucleus, I know as a result of this, what will happen. And that I can measure very precisely. That's what I'll do. There's one more there. Yeah.
One basic question. I just wanted you show the proton as a kind of rough sphere, this thing. So what is confining the quarks and the gluons inside?
You tell me the answer and I'll send you to take the Nobel Prize. Yeah, we don't know. We don't know. There are ideas, but there's a property called confinement. It's a profound thing that happens. We don't really know why the proton has the radius the way it is. Yeah, we know much about it, how the interactions are slowing down or becoming so part of the QCD, quantum chromodynamics, there are two components to it. We didn't understand before about 1980s and 1990s why the quarks and gluons are acting like as if they are free inside. If you go close to it, then they're almost free. So the difference, I didn't say much about it. You know, in gravity and electromagnetic theory, if two charged particles go away from each other, their force decreases, right? Yes, we know that, right? Gravity 1 over r square. In QCD, in the confinement of the proton, it increases. You take one quark and another quark, anti-quark, and you try to move them, it's like a rubber band. You try to stretch it, it's becoming more and more difficult. And at some point, you can't take it out of the proton, you know that because that's a property. The rubber band is willing to break, but don't let the quark leave. Once it breaks, it creates another pair of anti-quark and quark right there. So you're back to square one. Now instead of one rubber band, you have two rubber bands. Then you have a problem to study this. How do you do that? Yes, it keeps on happening, and that's also another way of explaining what the problem for theory is to calculate it. Every time you try to do a modeling of the breaking, you have to give up and say, oh, now I have two. So instead of solving one problem, you created two. You try to solve two problems, you create four. Unless, right? And theorists have a difficult time with this, even if they have computers, because everyone is going to create this. So, did I answer whose question was? Yeah. So that is what the thing is. So the free, so bring them close and they feel as if they're free. They don't even feel each other because the force is proportional to R. R is 0, the force is 0. You bring them together, they're happy. Bring them apart, then they get violent. But to get them to do apart, you need to put a lot of force on it. And that is the confining force. What dynamically generates it is not known. Yeah, but I think there is a prize for $1 million cash to solve that problem. Yeah, 1 million, 2 million, what is it? These days it might be 2 million, I don't know. Huh? Yeah. Yes, yes. It's $1 million. Okay, you take it if you want to take it. Yes. Yes, it cannot. Nobody has ever seen a single free quark. Nobody has ever seen it, and I assure you will never see it. Every time it tries to come out, it will have to pick up an anti-quark and become a pion or a kaon, as we were doing that in that picture. It's the glue that binds them all. That's why the title.
And there was an attempt at trying to unify all different forces.
Yes.
And they were using proton decay
Yes.
as one of the ways to look at.
Correct. And you know the difficulty. Proton damn thing doesn't decay. So it's difficult.
What implications does your work have on you?
Nothing on that front. It just gives me, the precise knowledge of the strong interaction is something that we will measure here. And that will only make the extrapolations of unification much more precise. Currently, he's talking about, you probably heard about unification of all forces. As electromagnetic became electroweak, yes? Electrostatic and magnetic became electromagnetic. Then electromagnetic and weak became electroweak. And now we have still two separate things remaining, which is gravity and strong interaction. The strong interaction is gluon dominating, and the gravity is, recently we know that it also has a wave. That means it has a graviton, a particle that does that, right? So he's asking, what does this imply for that kind of unification? Can we eventually, well, we can't really talk too much about it, except that I can tell you, the more precisely measures the strong interaction, the better extrapolations we will get. So that whenever we find someone with bright mind from this or other crowds will figure out what that unification is, he or she will have the right extrapolation to make those predictions. Uh-huh.
Does not the three-flavor NJL, which incorporates chiral symmetry, explain the ground state properties of nucleon like mass?
Well, yes and no. What we try to understand is the mass, total mass is known. The total masses of these quark, anti-quarks, or the pions are very well understood. The question we are asking is, what fraction of it comes from quark-gluon interaction, gluon-gluon interactions? That is still uncertain. Certain things we can figure out from lattice QCD, but certain things we still don't know. And one of the most important thing is the gluon-gluon interaction. So the total mass is known, some of the other things are known, but the glue-glue part of that mass is still not known, and it cannot be calculated accurately. And that's why we want to measure this. There was another there.
Sir, what gives the proton a boundary so that these gluons stops multiplying and starts merging?
No, the other way around. You should be asking what, the first part is the unknown part, the confinement. Why is the proton radius what it is? We don't know yet. If I understand confinement, I would tell you what the radius is, that what it is. But once you accept that there is confinement, which means, well, experimentally we know it is confined, then we can take that constraint out. And you say, you see, he was very careful in his Nobel lecture. What he said, he was playing with, not intentionally, but he was very careful in what he said. You see that? No, one back. He said, color charge in free space, or something to that effect. Small color charge in isolation. It's a key word there. And there is no color charge in isolation. Yes? You can never find a gluon or a quark in isolation outside the proton.
Sir, but in early
inside, yes, inside you have it. So the radius puts the constraint in order to increase the density. That effectively makes it crowded. It's like getting into a crowded bus, right? It's simply exactly that.
Sir, but in the early stages of the universe, before the formation of protons, there were only gluons and quarks.
Correct, you're right. And what formed the proton is again the confinement problem, which we don't know.
Thanks.
But we can keep on doing it in a reverse way and try to understand it.
Sir, we have one question here.
Okay.
And I hope,
There's one more there, I think.
no, I hope you're okay with taking questions outside during
Oh yeah,
tea.
sure, absolutely.
So then we'll end the formal Q&A session after this question, and you can discuss with him during tea.
Of course. No, there's one
The
more.
last question.
Questions.
So the question I had was, you mentioned that once the the photon comes in,
it becomes quark and anti-quark, which is again a colored, this
But
thing.
they are together colorless.
They're together colorless, but like when they get inside and sort of start interacting with the gluons and everything.
Yes.
Do they interact with quarks as well, which are inside? And is that accounted for when we do the
Yeah, yes,
experiment?
it is. Yes, absolutely. But normally everything has to go through the glue.
Okay.
Because the other quark which is sitting there will also see the radiation or radiate.
Okay.
Two charged particles in the proximity of each other will always radiate. That's a fundamental property of any charged particle.
Okay. So when it comes to the measurement, right?
Yes.
Because it sort of passes through.
Yes.
And then there's a chance that it will meet a quark or
Yeah, what we see is the final output, and we in the calculations we put it back. It's the effective interaction. It's not one and one.
Okay.
Yeah.
So is there any calculation in place to actually distinguish and then say this is?
You can, and I was saying, I think the previous question that came up, lattice Q-City tries to do that, and it does a decent job of any calculation that has a quark in it. What it fails to do very well is when you only have gluons in it, because that becomes much more complicated.
Thank you.
So there is just one more question online, which I'll end with. Are axions the key to explaining the proton radius puzzle?
I don't know that. I haven't heard anything that says axions keep the proton radius what it is, but I'm not an expert at that. So.
Okay. Then I guess we'll end the session here. I request everyone to please have tea before you leave, and the speaker is open to taking questions there.
Yes,
discuss there also. Thank you.